Welcome to another lecture of linear programming. We are in the last stretch of technical details, right? More of these math learning and doing simplex kind of thing. And after that, we will go to duality theory. As I told you in the email also, it's one of the most beautiful mathematical construct I have seen, and I'm very excited to tell you all about it. And after that, it will just be applications. A lot of applications in different areas. So I think every week we learn basics of some new field and then see how linear programming has made an impact there. Okay, but for today, let's finish our simplex method, and I think even this has very nice, clear mathematical ideas using convexity theory. So if you remember, forget about this. In general, what we know is that our feasible region of linear program is a convex region, right? It's a polyhedra. Now, that means we know that since our objective function is linear, the optimal will lie on one of the vertices, right? And the other thing is that the global optimum, local optimum is going to be the global optimum too. This suggests this nice algorithm. Pick a vertex, we might reach here, and again I haven't told you how to start with a vertex, but if we have a vertex, let's say we start from here, we know there is one direction where the objective function has to increase. In this case, it turns out in both directions our objective function is increasing, right? So this hyperplane is giving me the increase in the objective function. This is what I want to maximize. So now, if this is the increasing direction in this way I can go this way, and I am lazy, so let me put the short way, I reach this vertex. And then at this vertex, again, I always have an option to move towards the optimal. And when I reach here, I check in both the directions, my objective function is decreasing. Great, I have reached the optimum, right? This was the idea, and we saw a simple example, right? That simple example kind of demonstrated this thing with this standard form, and we will keep this standard form in mind. There are a lot of simplex methods, a lot of implementations. I am doing just one of it, but the idea remains the same. You travel from vertex to vertex, find the local optima. If you are at the local optima, you are done, happy, go home. Okay, this is what we are going to do, but we won't go home once we find the optima. We are going to have another class today after that. Okay, so this is the standard form. You maximize a linear function such that you have these linear constraints and the positivity constraint. Here, the number of variables is n, right? Number of constraints are m. That means B is a column vector of length m. With this in mind, we saw that under this standard form, it's easy to describe a vertex. There was a one-to-one relationship between vertex and BFS. We saw this proof last time, right? And just to remind you of what BFS is, a basic feasible solution is actually characterized just by a subset of n. Okay? You pick a subset of n. Once you pick a subset of n, the remaining part, B bar, I am calling non-basic. Okay? So you have basic part, non-basic part. What do you know? Everything in the non-basic part is 0, right? Also, AB is invertible. What do I mean by AB? Once again, A is an m cross n matrix. So you have, let's say, n variables here, and first constraint, second constraint, mth constraint. So every column in some sense corresponds to a variable, right? It is giving you the coefficients in the constraints. So then AB basically means pick all columns for basic variables. Okay? This defines my basic feasible solution. You might ask, oh, there is no solution here. There is no x here, right? I talked about basic feasible solution. I'm just giving you a subset of n. But we do have a solution here. Why? Right. Since AB is invertible, I know Ax is equal to B. This is by the definition of matrix multiplication. This, right? This is just how we multiply matrix and vector. And then we know that this is 0, so then xb is okay. So yes, a basic feasible solution is a feasible solution which have lots of zeros, but to specify it, I need to just worry about the subset. If I give you the subset, I have everything. Good. So now with this understanding, and if you remember the last time we did an example of how we moved from vertex to vertex, let's just formalize a simplex method. Okay. Questions about any of this? Okay, good. So this equation is actually pretty nice. I started with this, but then if I know this, it is telling me that every basic variable, sorry, what did I do? Okay, wait, yeah. So let me redo it. Let's say I have a basic subset which corresponds to a BFS, and let's say my solution here, the actual solution, is PBPN, right? But forget about the actual solution. At any point, I can write my equation like this. Right? What is this telling you? At this stage of the basic feasible solution, everything, every basic variable can be written in terms of the non-basic variables. Right? And this is something which we did last time, if you remember. Every time we moved from one solution to other, our basic variables are always represented in terms of non-basic variables, right? So I have that, and once I have that, I can change my objective function also to be C prime, say, let's say plus some, okay, some big constant C. Okay. What have I done? I had just rewritten my linear program. Haven't changed anything. I have just written my linear program in a nicer basis. You can think of it as doing row operations in your matrix A, so that my basic variables become diagonal. Right? You remember Gaussian elimination, right? What will happen if I am doing Gaussian elimination with basic variables? Basic variables are invertible, so I can make it 1, 1, 1 and everything 0 otherwise, right? So I'm able to write all the basic variables in terms of this. This is not a new linear program. This is the same linear program. You can think of it in a different basis or after row operations only. Okay, but what is the advantage? This gives us very clearly what is happening at this vertex, right? First thing is my PBPN comma 0. Correct? Because xn has to be, Pn has to be 0. So that means my PB has to be AB inverse B. And my objective value is, so I should say C transpose P, where C is the original C, this is equal to what do we know about non-basic variables? Yeah. Right? So the objective value at this basic feasible solution is just this constant which is appearing here. Okay? So this is the advantage of converting, again, when I say a basic feasible solution, it is the basic feasible solution here, it is the basic feasible solution here. But this form is much nicer. And this is what we did last time too. PB and PN is the actual solution. XB and XN I want to keep it for the variables themselves. PB and PN is the actual basic solution. So, actual solution at BFS. Right? And once I write it this way, it is very easy for me now to see, is there a direction which is increasing the objective function? Right? So let me just write down the two conditions. There is no sketch pen here, so let me just write down here. What do we know about BFS? The value of non-basic variables is 0 and AB. Very good. Right? And what we did by example, now we can see that it almost works in every case. Right? Now, is C optimal? How do we know that? Right? If all these coefficients are negative, right, then I know that. Good. So how to check local optima for BFS? Are all Ci primes negative, or let's say even less than equal to 0. So if they are all less than equal to 0, finish. If local optima is a global optima, we are finished. Question?
So wouldn't it be better to visualize that negative anyway, because that would be better for...
Again, you are getting confused between xi's and Ci primes. These are coefficients.
Yes.
So if xi's are all 0, even though this is 0, you can make xi to be anything, any delta. This is not going to increase the value, right? So yeah, don't confuse between Ci prime and xi, right? So now this is definitely our criteria for finishing, right? If we do not finish, what do we need from our intuition of simplex algorithm? Direction of progress, right? So how do we find direction of progress here? Whichever Ci prime is positive. If there are many Ci primes, take your pick. Start with take your pick. I will have something to say about it later. Okay, so pick an I such that Ci prime is strictly greater than 0. This is my direction of progress, right? Now, if Ci prime is greater than 0, this I will become my entering variable. What do I mean by entering variable? Entering in the basic feasible solution. Okay, so this now in this subset in the B prime, the new solution is going to be B union I, but then I need to remove something. I need to have a leaving variable also. And how do I decide the leaving variable? I want to make sure that the x remains positive, right? So now what is going to happen? All these things were positive. You had some constant, and then you had these x's. As you start increasing x's, right, you know that each of these are positive. Why? xb is a feasible solution, pb is a feasible solution, right? So this is all positive. We know that. So now this is all positive. Here everything is 0. As I start increasing I, one of the variable will become 0 first. That is my leaving variable. Again, I am writing this in informal way, but I am sure you can write down this mathematical equation in terms of the coefficient here and the coefficient here, the ratio of this coefficient to ratio of xi, right? Also the ratio, the coefficient of xi should be positive. If it is negative, then we are happy. Then we can just increase xi to whatever we want. If the coefficient of xi is positive in those equations, this divided by that constant, we want to take the minimum of that. That's how much I can increase xi, right? So you can write that formula, right? This is not, okay. So important point is, and we did this last time. We had 4 equations. We saw, oh, if I'm increasing x1, does this become 0 first? Does this become 0 first? Does this become 0 first? Whichever one becomes 0 first, that's my leaving variable. Okay. Now J. I have gotten my new BFS. Pick one. If the 2 ratios come out to be same, pick one and put that. Right. Now, once I do this, I want to make sure that I get the similar form for B prime now. But that's not very hard. Why? There is a single equation here where it is xj is in terms of non-basic variables, right? So there is an equation, yeah, good. There is some equation minus xi something. Just convert this into xi equal to, and now this is a substitution which you will make in every other equation as well as the objective function. So substitute to get the right form. Right? This will keep going at some point. Since why is it going to finish? Why does it have to finish in finite time? Finite number of vertices. Right? So let's see how good you understand this. Okay? So let me ask a few questions. What can I erase? And yeah, we play this game where someone answers, then they are out of this game. Then they can't answer the next question, then someone else answers. Yes?
Is it necessary for it to be minus xi?
Sorry, it has to be negative. If it is positive, then it's not a problem. It's some negative, some coefficient here. If it is positive, then I can increase xi and xj will never be a barrier. Right? Okay, so question. Why finish in finite time? Okay, so Dev is out of this game. Number of vertices, finite. What if coefficient of I is negative in all equations? I won't find J, right? It could happen that if you look at all these equations, the coefficient of xi is negative everywhere. I never said that this quantity is going to give you positive coefficients, right? Sorry, it's all positive. It's positive in all equations. Then what does that mean? All of you are out from the game. Okay, good. So this was right. Good. Always we are able to find entering variable. We are always able to find leaving variable. Okay. Now this is a nice question, right? Okay, if you look at this, what I talked about was once we found out that this was not a local optima, we had a direction of progress, right? And this direction of progress comes out to be in the direction of a variable, right? So we always got direction of progress for an axis, right? It is aligning with the axis, right? First, see that there is a problem here. There can obviously be shapes where the direction of progress is not aligned with any axis, right? For example, if my feasible region was like this, right? I cannot have x1 or x2 as my direction of progress. But here, my direction of progress always turns out to be a particular axis. That seems wrong. How can I? So, yeah, Pratush, wait, let's. Do you have an answer, it seems to me? No? Okay. You have a question? First you answer my question, then I answer your question. Okay. So, but is this dilemma is clear, right? That it seems like we are doing a great thing here. Every time we are able to move in the direction of an axis. But you are out of the game. So, axis means like either x1 I am increasing or just x2. So axis means x-axis, y-axis, right? I'm just increasing one particular variable, right? This is the direction of the axis. So why is my direction of progress always an axis? It doesn't seem to be the case in many places. Tricky question, I understand. Okay, so your final answer is correct, but I'm not sure whether you have connected all the dots. You need to say more so that I'm sure you have connected all the dots. Okay, anyone who are part of the game, so not part of the game also?
So we can, if there is any direction of progress, we can break it down into components.
That was I think that's what Kumar was saying. No, I will keep asking. Okay, after 40 years, you're allowed to ask this question multiple times. Okay, so yeah, anyone? No? I give you the answer. Is the axis here an axis in the original solution? No. We have changed the basis so many times. This is an axis now, right? So don't get confused by this notion that the equations written here and the equation written here are in the same basis. You have changed the basis a lot of times. So what the xi which seems to you to be the direction of basis now, it's some direction of basis depending upon 3 times AB1 inverse multiplied by AB2 inverse multiplied by AB3 inverse or something. Okay, so no problem, right? So this is not an axis originally. We have, or other way to say it is, we have rotated our axis in such a way so that our edges are aligned with the axes. That's another way better way to think about it. In the original way, we are changing everything, but in this one, we are actually just changing one axis. Okay, so what if quotient of I is positive and all? Oh, then you can just make xi to be infinite. Everything will remain positive, all variables will remain positive, and your coefficient in the objective function was positive, so your maximum is infinite. Oh, those were the only things, those were the only allowed leaving variables, right? Leaving variable was one of the variable whose coefficient was positive. If everything is negative, then we have a local optima, we are done. Yes, because we have to finish in finite time. If I have to increase infinitely, at some point I have to find a direction where I increase. Right?
It's not given that the physical set is bounded.
No. Feasible set is convex. That's all we know. Right? And now we come to Kumar's question, right? So, what have I not described? What case have I put under the rug and you did not bat an eyelid? Though that will help later, but that's not the problem. Huh? No. Oh, great. I'm already at the optimal. You want? Let me write it, huh? Yeah. What was it? C plus summation. Correct? And then what was the equation here? XB sorry here. ठीक है यार, तो चलता है. So again, you are roaming around the right solution, but okay. I said this is it positive or right? So is it positive or is it non-negative? Right? That's the only thing I know. It is non-negative. So what if my equation looks like xg equal to 0 I haven't ruled out that possibility, right? This corresponding constant could be 0 and there is a negative non-zero coefficient in front of xi. So now I know that I cannot increase xi. So I can switch xj to xi, that's okay. Xj, but what if this becomes a cycle? Right? So in some sense you are at the same solution, you are not changing the solution. You are just denoting them by different b.
Sorry to interrupt, but just wanted to confirm a bit this cycle. Like, at one point, xi was entering and xj was leaving. And
Correct.
at another point in between, xj will be entering and xi will be leaving. That is
There could be 10 variables.
yeah, for the basic case to begin with. That is what is denoted by the cycle, right?
So yeah, probably you can easily argue that it cannot be just 2 variables, but what about a cycle of 10 variables?
So it can be.
It can be
like
too.
that,
Huh.
but I'm just saying that is what.
That is what I'm saying, yes, yes. So then your objective function doesn't increase. You are not saying that you are at a local optimal. What if I stay in that vertex? I'm just roaming around in the basic feasible solutions at the same vertex. This is what we call degeneracy with the whatever is the right spelling. Okay? Except this, have I covered everything? Let's jog your memory. What have I not told you in the implementation of everything? Happy? Huh? Selecting the first. These are the two things which are remaining. Everything else, I have either given you an idea or explained to you how we will do this. This is a complete description of simplex algorithm except these two parts. And you realize what is degeneracy? Cycle of basic feasible